Hi there, everyone. My name is Mr. Los. Thank you for watching, and I just want to thank everyone for their hard work so far. The very fact that you're sitting here watching this video at this moment shows me that you're working really hard, and I appreciate it. So what I'm going to do is go over some stoichiometry involving the ideal gas equation, and it comes from this page. It would be in the workbook supplement, like the extra section, non-STP gas stoichiometry using the ideal gas law. So we started off last week. We worked with stoichiometry with the ideal gas, assuming things were at STP, where 1 mole is always 22.4 liters. And basically what that is, it's kind of a shortcut way to not have to use Pivner at the ideal gas equation. But the fact of the matter is, in real life, you're very rarely at STP. STP is 0 Celsius, STP is 1 atmosphere pressure. So basically a freezer in Florida is when you're at STP, but most other times you're not, especially here in Colorado where our pressure is always lower than that. So we're going to look at a couple problems here, and there's a tip here to help you get started. What I would suggest that you do is literally write out the variables for the ideal gas equation down the side like that. And as you pick your way through the problem, see if you have enough information to solve. So to solve any kind of math equation, we need all the variables but one. If we have enough information to solve, in other words, if we have all the variables except for one, we're going to do Pivner first, the ideal gas law first, and do some stoichiometry second. Otherwise, we're going to do it the other way around. Another thing that's important is remember that you can only put stuff relating to a gas. So think very carefully, and this is kind of true to this whole unit. There's different things you do depending if you got a solution, or if you have a gas, or if you have a solid. All those require a little bit of different techniques. So in this case, I put CO2 ahead of time because I know that's what this question asked for. So that's what we really need to focus on. Let's read it carefully and figure out what's going on here. Carbon dioxide can be produced by the decomposition of sodium bicarbonate, otherwise known as baking soda. The reaction also produces water and sodium carbonate. What volume of CO2, and CO2 of course is a gas, so we can tell already that that's what we're going to be solving for, can be produced by decomposing a 35-gram scoop of baking soda. Now that's sodium bicarbonate. So that's not directly related to CO2, so I can't put anything in there yet. The temperature in the lab is 20.5. So 20.5 degrees Celsius, but of course I have to change that to Kelvin, so I add 293 to get to my Kelvin temperature there. And then the other information that I have here is that the pressure is 0.878 atmospheres. So I can put that in for my pressure. Okay. We can always put in R because that's a constant. So that we can just always fill in no matter what. Now what you're going to notice here is we have two variables missing. I've put in everything that I can from the problem. There's two variables missing here. So that means I need to do some stoichiometry first, and then I can solve and do the ideal gas equation second. And what I need to solve this is I need moles of CO2, specifically CO2. So again, keep track of what you're talking about as you move through the problem. Now I can do that because I do know the mass of this stuff, and I can just do a mole to gram stoichiometry problem. Gram to mole stoichiometry problem. And so what I'm going to do is I'm going to start with 35 grams of the baking soda. I'm going to add up the molar mass, 1 sodium, 1 hydrogen, 1 carbon, 3 oxygens. That is 84.01 grams. That goes on the bottom because what goes up must come down. And that is 1 mole always when we're using masses. Now the next thing, sorry, my writing's bad here. I'm writing vertically, but that's NaHCO3. So the next thing I need to think about is the mole ratio. And it's my experience that by far the biggest mistake that people make in these problems is they forget the mole ratio. And sometimes it doesn't matter, so you can get complacent, right? Like you'll get lucky, like the mole ratio is 1:1 and you get the right answer. But we need to be really careful and always make sure that we think about that mole ratio. So that is 0.208. Once we solve that out, that's 0.208 moles of CO2 will be produced from that much baking soda. Okay, so now that's the hard part right there. What we got to do now is actually just solve this equation. I want to solve it for volume because that's what the question is asking me for. So I divide both sides by P. So V equals nRT over P. and just need to plug in the stuff. So we're going to plug in the moles that we figured out right there, 0.208 times 0.0821 times the temperature in Kelvin, which is 293.5. I'll put that over here, 93.5. Apologize about the handwriting. And then divided by the pressure, which is 0.878. So just plugging in the N, the R, and the T over the P. So it's those three things multiplied together, divided by the P, and we're going to get 5.71 liters. Okay, so that's problem one. Go back, feel free, rewind, take another look if you didn't understand, or ask me a question, send me an email, come by to office hours, etc. So let's try this one. Number two, a science teacher, and I so wish that I was here. I would certainly do this demonstration. This is my favorite demonstration of all time, what's being described in this problem, and I would do it for you if we were in school in person. So like I said, literally, we're going to write out the variables for the ideal gas equation, just like I'm doing here. And we're going to pay attention to what is being discussed in the problem in terms of a gas. And in this case, looking ahead, it's hydrogen gas, just because I've looked at this problem already. So that's how I know that. So we're trying to fill a Pringles can with hydrogen gas, and it gives us the volume of the Pringles can. Hydrogen will be produced by reacting zinc metal with excess hydrochloric acid. What is the minimum grams of zinc? So that should be added. So we're trying to make 1.05 liters of hydrogen. That's what we're trying to make. And the temperature is 25 Celsius, but we're going to add 273. That's a 2. So that's 298 Kelvin. And R, we can always fill that in with its 0.0821. The pressure is 0.94. So notice we actually have enough variables, and that was what I said. The general plan is you write out the variables for ideal gas equation. If you have enough variables to solve, you're going to have to do ideal gas laws first and stoichiometry second, otherwise the other way around. So in this case, we're going to use the ideal gas law first, and then once we do the ideal gas law, we're going to do some stoichiometry. Basically, where we're going with this is going to tell me moles of hydrogen. Once we know moles, we can just do some normal stoichiometry to get to the mass of zinc. So solving the ideal gas law here for N, so I'm just rearranging the equation like I did before, doing some algebra to solve for N. So PV divided by RT equals N. Put the information from the problem in, 0.94, and then the volume is 1.05. And by the way, all the units are right. The pressure is in atmospheres, the volume is in liters, so we want to make sure that we check that as well. 0.0821, and then 298 Kelvin. So if you put this in your calculator, do it just like that, especially the bottom term. You need those parentheses around there. So what this tells us is we need about 0.0403 moles of hydrogen to fill the Pringles can. So that's moles of hydrogen. Now, where we're going to go from here is it's going to be a mole to gram problem. So we're going to start with the moles. And once we know moles, we always do the mole ratio next. It is a 1-to-1 mole ratio. So there's 1 mole of hydrogen for every 1 mole of zinc. And now mathematically, yes, this doesn't change anything. And by the way, that's a 4. Mathematically, this doesn't change anything. But it's just so important to think about that mole ratio. We want to make sure that it's there every single time, so that when it does matter, we don't forget about it. Because, like I said, the biggest source of problems on this is forgetting about the mole ratio. So anyway, we got 0.0403 moles of hydrogen. It's actually going to be the same number of moles of zinc. Then we're going to go back to a mass of zinc. So zinc's mass goes on the top, moles on the bottom. So it would take about 2.6 grams of zinc to make that much hydrogen. 2.6 grams. Okay. So on this third one, what I would like you to do is take a look at it and see if you can figure it out. It is not balanced. I'll let you know that. We need 223 here to balance this. I'll just save you that step. So I'd like you to take a look at this. Again, the general plan is write out PV and RT. think about what it's talking about. Notice it's talking about inflating this bag. This is a true story. Airbags are basically like bombs. They really are. If you think about an airbag, it's kind of an amazing piece of technology. You need to have a bag that inflates in just a fraction of a second. While the person who's driving, their head is moving towards, they slam into the steering wheel after they've run into something. So it needs to inflate in a fraction of a second, and actually it needs to start to deflate a little bit, because if you run into a rapidly inflating bag, it's almost as bad as hitting the steering wheel itself. So it is basically like a little bomb. It's something that produces an awful lot of gas quickly, and what fills the gas is nitrogen. So when it says how large will the airbag inflate, that is asking for the volume. Okay, volume is how big something is. So that's just a tiny bit of a start. So remember, the strategy is try the variables, see if you can find enough variables for the ideal gas equation to solve it. If you can, solve the ideal gas equation first, do stoichiometry second. Otherwise, the other way around. Do stoichiometry first, solve for the ideal gas equation second. So what I'd like to do is pause it, see how far along you can get into this, and then you can unpause it, and I'll walk you through my calculation. Okay, so here you go. When you solve this problem, when you look through it, you'll find that you can figure out everything initially except for the volume and the moles of N2. So we are going to do stoichiometry first, and the goal is going to be to find moles of N2 so that we can put it there. It gives us a mass of sodium azide, which is this. Change to moles of sodium azide, mole ratio. Now we're going to stop at the moles. We wouldn't want to change it to a mass of N2, right? Because we need moles in the ideal gas equation. So we stop at the mole ratio part. And then from there, that tends to be the hard part. From there, we just need to do a little bit of algebra, rearrange the equation to solve for volume, plug that stuff in, and you end up getting about 38.5. Seems to be a decent size for an airbag. Okay, well, thanks for watching. That's some examples. So there's practice in the workbook, and there's more practice of these type of problems here. Now, one thing I've noticed about these kind of problems is they do occasionally give you pressures in a different unit. What I'm going to do is, by the time you guys see this, on the online version, I will have changed those pressures. I'll have converted those pressures to atmospheres. So you'll be able to look at that. Really, you just divide by 760 to change the millimeters of mercury. But yeah, you can't use, this is our pressure unit here that's given in this problem, and you can't use millimeters of mercury with the version of the ideal gas equation that we've learned. So these would be great practice problems. Again, I'm going to convert those pressure units, but let me know, as always, if you have questions. Stop by the office hours, which at least for my particular class are on Tuesdays at 12:15. So thanks for watching, folks, and we'll hopefully see you soon.